Question number 7 is more organic chemistry synthesis. So they started out by talking about methyl benzene. So it's just one CH3 on the methyl benzene. And then step 1, they go to M, we don't know what is M. They go to N, we don't know what is N. And then they go to step 3. Step 3, we get this thing which looks a bit different, CO2H there, and then we get a NH2 there. So something has clearly changed. We need to think about working backward. From here to here, we have seen the CH3 there becomes CO2H. So we can think about oxidation of alkyl side chain. But the order of doing things is very, very important because as stated in your data booklet, if this is CH3, a CH3 or any alkyl group is 2,4,6 directing. And if you have a CO2H group, it is a 3,5 directing. So we look at where we are here. If we direct from here, then our substitution will be here, here, and here in green. Whereas here, we can see that these are not our green position because if this is position 1, this is 2 and 3. So this is 3 directing. So we can see that if I draw that color, this is in position 3 relative to the CO2H. So meaning to say if I do my NO2, which is my nitration, and then reduction, that means I will direct it onto position 3 and 5 if I have CO2H, but the NO2 will go onto 2, 4, and 6 if I have got a CH3 to begin with. I want it here, so I think I will do my oxidation first. So that means M is going to be CO2H, just like that. I think there's going to be M there. Okay, let me just put it in a bracket. Well, I mean a box, not bracket. I don't know why I keep on saying bracket throughout this tutorial. Anyway, so now the CO2H will direct onto position, if that is position 1, then it will direct substitution to position 3 and position 5, which is what we are hoping for. So this is going to be your nitration. So your nitration comes second and not goes first, because if nitration happened here, it will go to 2, 4, and 6. So decision really, really matter. So this is going to be N. And when you have nitration, that box doesn't look so good. That box looks better. So this is your nitration product there, and then from there to there you can just do reduction of the nitro group and you can get the phenylamine. Draw the structure of M and N. I have just done that. I have identified the type of reactions. So for part 2, step 1, what is your reagent and condition? I'm going to oxidize the alkyl side chain there. So our reagent and condition has to be the acidified KMnO4 or acidified MnO4 minus, and then you have to reflux that as well. Step 2 is your nitration. So nitration of a benzene group, that means it's a highly deactivated group. As this is not phenol, as this is not phenylamine, I cannot just use dilute nitric acid, it will not work. I need fairly extreme condition. I need concentrated sulfuric acid. I also need concentrated nitric acid. You should have learned how to write the balance equation to show the production of the NO2 plus electrophile. It's one of those things that they like to ask you in this kind of topic. And of course, I need to reflux that as well. And the reflux temperature usually is around 60 or 50 degrees Celsius. Very particular for this thing. What happened then is reduction. So step 3 is reduction. So reduction of the nitro group is very, very particular as well. So it can't use the normal reducing agent. Reduction of the nitro group require the use of tint and also concentrated HCl. And you also reflux this. By right, if you want to get phenylamine, if you do it acid reflux, you're gonna get the protonated version. That's why some textbook or some marking scheme, they will say after this reaction, then you would add NaOH in excess, because you want to get back the phenylamine. Otherwise it will get protonated to give you the salt with the NH3 plus and the Cl minus as the phenylammonium salt. However, I think most of the time in Cambridge exams, it's very rare that I expect this from you, but you should be aware that this is acidic conditions and this is weakly basic, but it is still basic. Okay, so this is just one of those things that I can add in order to make my answer as fully as possible, because I want to get the free base. I don't want the protonated base after all. What question was this again? This was question 7. So paper 4 is really long, isn't it? Question 7b part 1. So I'm looking at serine and lysine. So this is amino acids. So I'm thinking about dipeptide. When two amino acids condense together, I will get a dipeptide where I will get this peptide bond, which is also an amide. So all peptide contain amide bond, but not all amides are peptide. You only get peptide when you have amino acids condensing together. So what could be present in this product mixture? So they say serine, lysine, but of course I could also have lysine, serine. Okay, so we draw from nitrogen to carbon terminus. So there's just a standard in biological chemistry or biochemistry, N to C terminus. Someone got a Nobel Prize for that particular idea, which of course they managed to prove. I'm not a big fan of biochemistry, so I'm not very good at the underlying concepts, but I can do the chemistry bit. So serine is started out by having what is this, HO. This looks weird. Let me draw the H2N first, just like we would draw normal carboxylic acid on the right, the H2N on the left. Then we have an amino acid with a H, and we have a CH2OH, so CH2OH like that. And we are trying to condense that with lysine. So lysine again is this amino acid, and I have got this thing which is CH2, 4 of them, and then NH2. So this is my side chain, CH2, and then 4 of them, NH2. I will do serine and lysine first. So let's do that first. So what happened is I do condensation. So it will lose the H and it will lose the OH there. So draw the structure, and I should display the functional group, just like the polymer just now in that condensation polymerization question. We got a display at the particular amide linkage there. So if I have that, so the H2N, that OH just stays there, that carbon, oxygen, and then N and H, and then I can just draw skeletal or whatever I want for the rest. I guess I'll probably just draw skeletal to be complete as possible. So there's my CO2H, and I got CH2, 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 and H2. Does that look good at all? No, that could be better. So there's 1, 2, 3, 4, CH2 4 times, and then NH2. I got a CO2H terminus, I got a H2N to CO2H terminus. I've got my amide linkage, so this is my amide or my peptide linkage. This is lysine. Okay, so that's your first one. And the other possibility would be what was it just now? Lysine and then So if I draw this one first, actually I'll just copy both of them because I can just swap the position later on. Okay, now I will swap the position because the line comes first and then the cell goes later. I will cancel out this green coloration there, and now I have this losing the OH there and losing the H from the H2N there. So what I'll get is H2N, and then I get C double bond O, NH, and then OH there, and then CO2H. Here is my CH2NH2, so 1, 2, 3, 4. Is that correct? 1, 2, 3, 4. Yep, that's perfectly fine. Yeah, I mean, that's it really. So we have gotten our final product. I could draw skeletal for the rest of them as long as I display there. So there's an amide or your peptide linkage there. So they want the two things in the box. I haven't drawn it in the box, but this is going to be your lysine and serine linkage, whereas the previous one was your serine and your lysine linkage. Hope you can see that these and these are two different products, okay, but both of them are from the N terminus to the carbon terminus. For that, you get 3 marks. And now you want to have, what do we want? C9, H12, and 2O5. What in the world is that? Let's read the question. In the next part of this question, part B, so we are told something about serine and lysine. So if we have serine, we have HOCH2. I think it's best if I just draw it in the normal way we draw amino acid, which is like this, H2N and then CO2H, and then we have CH2OH like that. So if you total the number of carbons, so there are, you can have a look at the structural formula given. So CH2, CH, NH2 twice. Nope, sorry, NH2 just on its own. There's 3 carbon, and then there is 1, 2, 3, 4, 5, 6, 7 of hydrogen, and there's 3 oxygen, and there's 1 nitrogen. And now you have lysine. Lysine there, if I draw the normal way I draw my carboxylic acid. What's wrong with my pencil actually? That going to that, and then I have CH2, 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 and then NH2. So I have 4 of this CH2 as my side chain. So H2N, H2N, CH2, 4, CH, NH2, CO2H. So if you total the number of carbon, there's 4 carbon there, 5 and 6, so there's 6 carbons. Hydrogen, there's 2 and there's 8, so there's 10, 11, 12, 13, 14, so there's 14 hydrogen altogether. There's 2 oxygen and there's 1 nitrogen. Don't know why my hydrogen is appearing a bit dodgy there. If you read this question carefully, this part 1, what do they want? They want 2 structural isomers that could be present in the product mixture. So you have product mixture, but be very careful about reading the molecular formula, C6H12N2O5. C6H12N2O5. Looking at that, so 6 plus 6 will give you 12. This is molecular formula, which is already the actual number of atoms, So cannot be 6 plus 6. 6 plus 3 will give you 9, which is more than 6. The only way you can get 6 will be 3 plus 3. So we are looking at serine plus serine. But then, if I am just looking at condensation between the H2N and the CO2H, then I'll just get 1 product. Am I correct? Let me see. Usually when we condense them together, when we do condensation, C3H7O3N, if I add another C3H7O3N, if I total the number of carbon is 6, if I total the number of hydrogen is 14, and then O6, and then N2, I need to take out H2O because it's a condensation reaction. So if I take out H2O, so I can cross out 14, become 12. If I take out another oxygen, O become 5. So that is how I get 1 H2O and 1 of these. So I need to do 1-time condensation. The question is, what do I do here? 1-time condensation. Well, what are the 2 possible products? You must show the 2 functional group. So display functional group. I can see that you can get amide because this H2N and the CO2H can condense together. It could give you a dipeptide. So serine and serine. So you could get C double bond O and H like that. So there is your amide, or there is your peptide, and then there's your carbon there and your carbon. So looking at that, there's a carbon, it's got a CH2OH. So that carbon there, let me see, if I draw skeletal there, the carbon there has got CH2OH, the carbon there has got CH2OH, and I've got CO2, nope, not CO2H, but NH2 on that side. So it uses a CO2H on the other side to condense with another NH2 on that side. So this side cannot be NH2, but it is a CO2H. if you work out the molecular formula of these, you would definitely get C6H12O5N2 because I've kicked out a hydrogen from the NH2, I've kicked out the OH from the carboxylic acid. Kicking out one water will give me one time condensation of these two things which are the same monomer coming together to give me this product after one condensation. The other product could be an ester. As you can imagine, you have an OH, you have a carboxylic acid. So if I have one of these, and I can draw like this, and then another one of these on here. So you can imagine that you lose the OH and lose the H there, such that your product is going to be an ester. So if I draw an ester first, C double bond O and O, and there's going to be an ester there. So if I draw my amino acid first of all, so this thing is going to look exactly the same. I use the carboxylic acid, loses the OH, and now I have the oxygen from the alcohol, okay, because it loses the H, and this is bonded to the carboxylic acid as well as the NH2. So that is your NH2 and CO2H, your amino acid. It's got a CH2OH that now condenses with the carboxylic acid from this particular amino acid, which has got CH2OH, NH2, and the original CO2H there. Okay, so I hope that makes sense there. That is your ester functional group there. Okay, so I have fully displayed my ester functional group there. I don't want to break my ester functional group, so I'll just draw it like that. I just need to fully display at the ester as well as at the amide functional group, so I think I'm okay there. Next up, what do they want? It's 1 mark for predicting. Okay, so this is B part 2. Now I have C9, H19, N3, and O4. If I have C9, it must be 6 carbon plus 3 carbon. Remember just now, 6 carbon, and this is 3 carbon. So the 3 carbon was serine, and the lysine was 6 carbon. Serine was 3 carbon, lysine was 6 carbon. So remember, you could go from N to C terminus. So meaning to say, don't know why they keep on doing that. So N to C terminus in a way that, you know, H2N there and CO2H there. So what we could have, let's see, we could have a lysine, serine. We could have a serine and lysine. So that should give us 2 possibility there. However, they're asking for the possibility. So you could have carbon to nitrogen terminus, meaning to say we will draw with CO2H there first, and it will have NH2 going that way. Again, we can have lys and then serine, or we can have serine and then lysine. So these are the 4 possibilities. As you could see, if you draw them out individually, then, you know, N to C terminus is different from C to N terminus. This is the usually accepted convention by biochemistry community. It's not saying that this doesn't exist, because this question is predict the number of possible different structural isomers. So there are 4 structural isomers that are possible altogether as a result of this combination, the lyser, ser-ly, going from N to C, C to N, but obviously 9 carbon is a combination of 6 and also 3 carbon there. Part C, so we have this, we have this big molecule. So if I just draw them out very quickly, so skeletal formula, I can easily draw them very, very quickly, because yeah, it's just the beauty of skeletal formula. Is so that people can draw them easily without having to think about a lot of things to begin with. Okay, now we need to label each chiral center. So chiral center mean a carbon bonded to 4 different groups. These are formed from, well, this got a couple of chiral center. I can show you where it is. There's one there, which is chiral there, and there is another one there, which is chiral, and there's no chiral center there because this is a CH2, because carbon from 4 bond, so there's 2 hydrogen there. They say label each chiral center with an asterisk, not with a circle. I've labeled with an asterisk there. No chiral center there because CH2 and CH2. No chiral center on this carbonyl carbon because they are not bonded to 4 different things. Now you have complete acid hydrolysis. when you have acid hydrolysis, then your amide will break. Your amide will break. Let me show you if I just copy paste that, because I don't want to destroy that diagram. If I just remove that Chiral Center first of all. So you have an amide there and you have an amide there. So I'm going to break there and I will break here. So what that will give me is H2N, CO2H, like that. And what this middle bit will give me is H2N and then CO2H, like that. What that last bit will give me is HO2C, or I can draw the skeletal formula. And then there's NH2, that will give me CO2H. So what is different is this amino acid hasn't used this carboxylic acid on the main carbon there. Instead, it has used the carboxylic acid on the side chain in order to form amide with this particular H2N there. So what can we say? Oh, I just remember one thing. I think I've made a mistake here. Because this is something with the NH2 on the side group. I just remember it. This is something with the NH2 on the side group. So we are still looking at nitrogen to carbon terminus. Carbon to nitrogen is not allowed. Okay, so we are still looking at that. But this is nitrogen to carbon terminus using side chain, using NH2 on the side chain. So I think it's very important that I go back and correct this thing. So I beg your pardon. So it is still 4 structural isomers. I just remember that when you have extra side chain, then this thing can also form amide with your other group. So it's still something from lysine to serine, something from serine to lysine, but this is using the NH2 on your side chain instead. Okay, so I hope that makes sense there with that correction there. So I will just very quickly move forward. And back to this question. Okay, so back to this question, because this reminded me it can use the other extra CO2H to form an amide with the H2N there. So what we have there, we have draw structure of 3 products formed after complete acid hydrolysis. I have just drawn the 3 products. Okay, however, we need to consider the fact that we are in acid hydrolysis. So that means this is a basic group. So that means you will not get NH2, but instead you get NH3 plus, okay, because you are in acid hydrolysis. Acid hydrolysis means at the end of the reaction, all your basic group, all your alkaline group is going to be protonated. So there's going to be H3 and plus there. We are not told on what is the acid used, so I can't tell you the counter anion, but the nitrogen bonded to 4 different groups. Nitrogen bonded to having 4 covalent bonds is going to be plus charge, just like ammonium ion there. Okay. Last but not least, onto the last part of this question, part 3. By referring to the structure of glutathione, why is it soluble in water? So if we look at the structure of glutathione, it has got the OH, it's got the OH, so these groups there can form hydrogen bond with water, and therefore it makes it soluble in water. So is it gluca or gluta? Glutathione has 2 hydroxyl group, has 2 OH, and how many NH group does it have? NH2, that can also form hydrogen bond, not the amide, but this one, the amide, can form hydrogen bond as well there. So the NH2 there. This nitrogen, the lone pair is actually delocalized through the pi system, so it's not exactly available. So this NH2 definitely can form hydrogen bond as well. And one NH of the amine side chain, they can form strong hydrogen bond with water molecule. So if they can form strong hydrogen bond with water molecules, it makes them soluble in water. Therefore, make them soluble. Can't even write that properly. Make them soluble in water. So that marks the end of that. How many marks is that? 13 mark question. And we're ready to move on to the next question. Phew.